So the next talk is from Georg Moser from the University of Innsbruck on automated expected value analysis of recursive programs.
Okay. What just happened? I tried it out before, so same issue as Joseph's. Okay. Okay. Yes, everything's fine. Okay. Thanks a lot for the introduction. My name is Georg Moser, and this is joint work with Martin Avanzini and Michael Schaper. So I'm going to try to explain to you something about expected value analysis. And we have seen lots of many interesting talks already, very exciting techniques. So I tried to lower down the temperature a bit and do a very, very simple example. Suppose I have a number of pins given, and I want to throw balls at them. And I'm not that bad, so I will throw at least one of these pins with each throw. How many balls will fall on average in a given bin? How do I solve this? Well, I can try it out, but probably the session will not last long enough so that I can do that. I can read it up, or I can ask ChatGPT. Eventually, all three will agree on the same answer. The expected value should be n divided by k, which is the expectation of this return value. Okay, what has this to do with programming? Well, let's put this into a program. The left example we took from the literature is just recursively programming exactly this question, and the right thing is the example we use as motivating example throughout the talk. So let me explain this example to you. It's a recursive procedure. We branch whether the parameter to the recursive call is greater than 0. If yes, then we recursively call balls on n-1, get the number of balls if we have thrown n-1 balls. Then we do sample from a null distribution, and we update the number of balls accordingly, and we return. That's it. Now, the paper is by Vasilenko et al., and it's a very nice paper doing lots of nice things. And in particular, they interactively prove that exactly this bound that we've seen before, or this value of the expectation of the number of balls, is p times n, interactively in a refinement type system. And our question was, why do things interactively if we can do it with a push button automation fully automatically? So if you start our tool and you run it on the example on the right, it will just tell you exactly the bound I just gave you in a couple of seconds. So what were the contributions of this work? We start with an imperative language in the style of Dijkstra's SCADA programming language, or in the style of Andy's conditional probabilistic conditional probabilistic programming language, however, without the condition. So there is no conditioning now in this talk. And in addition, recursion. And we throw in the semantics, and we can be expectation semantic again without conditioning. What did we do? We translated this expectation transformer in the semantics into a term representation, and we automated the whole thing. The automation has been subject to the artifact evaluation. It has been deemed available and reusable. So if you forget everything about the talk, just go onto Supplementary Works, click on the link, download the tool. It should work out of the box, and you can just play around with it. A few words more about this term representation. So we follow, in principle, this expectation transformer semantics quite closely, but we have to do something different for procedure calls and loops. I'll say so in a moment. Namely, the reason is that those will require the definition of fixed points, high-order fixed points, and they are uncomputable for us, so they are too expensive, so we have to do something different here. So let me now briefly explain how this works in practice. Of course, I'm relying on a lot of details, so please have a look at the paper. So this is our language. I only have time to look at two conditions or two commands here. Namely, we'll look at sampling and procedure calls. So what does sampling mean? We update a program variable according to a certain distribution, which is built in, as we have already seen with this Bernoulli sampling from Bernoulli distribution. On the other hand, we can have procedure calls or recursive procedure calls where we take an arbitrary number of, finite number of parameters, pass it to this procedure, and return a certain value and update again the corresponding program variable. Note this has this kind of sampling instructions because those values could be obtained probabilistically. In addition, we have dynamic sampling, so the sampling need not necessarily be just in a constant as we've seen here in the Bernoulli distribution, but could come from a program variable as a parameter. And it allows nested loops, non-determinism, and crucially recursion. And of course, not necessarily tail-recursion. So a few words about the semantics. A memory is just a mapping from the variables to the integers. As I said, it's based upon Dijkstra's predicate transformer. It takes ideas from Kaminsky's expected runtime transformer, which calculates the expected runtime of programs, of such programs. And this is suited to the expectation transformer in the spirit of McIver and Morgan's weakest pre-expectation transformer. So what is this thing doing? We have already seen expectations today earlier. So we take a non-negative real-valued function f on memories, which we also call a continuation, and we return the expected value of f after the execution of the command C in terms of the initial store. Instead of giving you the definition, I'm trying to explain this intuition on two examples, namely on sampling and recursive calls. So for straight line programs, the calculation is straightforward. Let's look at this part of the program where we have sampled from the Bernoulli distribution and updated the program variable b. What does this mean? Well, the value of d could either be 1 or 0, 1 with probability 1/5, otherwise 0. And then we update the program variable b accordingly. So meaning that the expected value of b is with 1/5 b plus 1, or it's b. That's it. And that's exactly what the expectation transformer is doing. In a case of loop and recursive procedures, a bit more complicated, namely we have to handle higher order fixed points. How does this look in our example? If I now look at a complete program, which is recursive, I take an arbitrary continuation f, and I want to have the expected value of this. What do I have to do to figure this out? I have to follow the structure of the program, so I have to take into account the branching again, the branching that either I do a recursive call or not, and then I have to take into account the expectation transformer with respect to the continuation after the recursive call, which has changed, which has changed exactly the form of the straight line problem that I looked at before. As you see, this fixed point equation is recursive in the expectation transformer itself, so we have to solve a fixed point. That makes it complicated, but by hand we can do it and we get exactly the same bound, namely n divided by 5 from before. Now, what are the challenges to automate this? Well, concerning recursive procedures and loops, the definition of the expectation transformer is in a sense recursive, as we've just seen. And we also have to take care of the call stack appropriately. What do? We have to change this higher order problem to a first order problem. That means for each procedure, we represent the function of the expectation transformer as a pair of first order templates, namely as the function h and k. H represents the post-expectation, k represents the pre-expectation, but the idea is that h upper bounds the expected value and k upper bounds the continuation. This expected value is conditioned on. So we can then set up linear, in this case, linear templates, namely h will be dependent on the parameter of the Bose procedure, and k will be dependent on the parameter of the program variable b. In addition, we have these x represented logical variables, which morally represent the sort of framework very similar to what we have seen in John's talk earlier today. Now, a very, very short, brief look at how does this look in the definitions. So this is the syntactic representation of expectation transformer for sampling and for recursive calls. Sampling case, again, is doing pretty much the same thing as I just said. We sample from a distribution. The procedure code now takes into account these templates that I spoken of before and substitutes them suitably, and also adds certain constraints that make their working proper. For a while, and non-determinism, we do the same thing. We add certain constraints that will govern their working. We can prove a soundness theorem telling us that this approximation is really an upper bound to the expectation, to the expected value of our continuation. So the inference algorithm is sound. Okay, now how do we now automate? We take all these constraints together and ship it to SMT, and that's it. Now, for our example, this would mean that we come up, for example, with the following upper invariant for this upper bound on the return value, expected return value, where we see here in the constraint, thank you, again, reappearing the notions from the body of the recursive call and also these conditions on the recursive call and some additional side conditions that we need in the transformation, the representation. In addition, to make this more scalable and more efficient for nested loops, we also incorporate earlier work that we had a modular cost analysis for probabilistic programs. Now, how do we evaluate this? We looked at various work in the literature, and I tried to differentiate them on the level of automation given and on the methodology used. We used two different variants of papers, namely one on invariant generation, where quantitative invariants were thought, and on cost analysis. First paper we looked at was Cator et al., which was a paper on linear invariant generation. The technique is semi-automated, so you need some user input, and it works on templates as methodology. Then there's a paper by Schaper et al. Again, this is based on templates, but now it's fully automated, and again, invariants were thought. It's a more recent paper by Wang et al., where, among other things, also an invariant generation technique was developed, again, fully automated, and again, based on templates. And there is also very recent work by Bao et al., which is also focusing on invariant generation, but this time not focusing on templates, so not prefixing our bounds, but trying to learn them in a data-driven form. All in all, this gives us 35 examples. Then we looked at cost analysis, the paper by Kaminsky I already mentioned. This is a very nice theoretical paper, not giving any kind of tool, but so there's no methodology based on anything, it's just theory. And then there's our work, which is again fully automated and based on templates. Additional 9 examples. From those, we added again 9 examples, so we have a testbed comprising of 53 examples in total. Out of them, we can handle 94 fully automatically, and the whole testbed runs in 5 minutes. And the precision is comparable to those works I mentioned before. This is a bit surprising, because invariant generation is, of course, a different problem where we precisely want to pinpoint invariant while we only compute upper bounds. Still, more often than not, our upper bounds are actually precise. Now, the motivating example I've given here cannot be handled by any of the tools of these techniques, because none of them supports recursion, at least not this non-tail recursion. So we also compared to methods and tools from function program paradigms where the expected cost analysis of recursive programs have been done, in particular work by Atlas and Rammel. Atlas cannot directly encode the example and produces a non-optimal bound, and Rammel cannot handle the example. So also in this case, our tool has some advantages. With this, I thank you for your attention and I open for questions.
Questions? Tiredness. Is there a question?
No,
okay, so I was just looking at the last slide. If everything is finishing in like 5 minutes, right? Like, what is the complexity of these benchmarks that you are testing in terms of
how big they are?
Yeah.
Yeah, those programs are typically rather short, so few lines, 10, 15 lines, something like this.
Okay.
So it's, as I said, it's 53 examples running all in total, and this needs 5 minutes. If I remove 2 very complicated examples and the examples that we cannot do, we can even do it in seconds.
So is it possible to also stress test the system a bit by trying larger examples?
The tests come from the examples in the literature that I
Yeah.
before?
But are there like bigger benchmarks that might?
No. We tried really everything to find examples which are recursive. As I said, we haven't found any ones, probabilistic ones. And if we are only focusing on this kind of probabilistic programs where we only do some coin tossing or some random choice in the middle, then there are not that many examples in the world. So that's the only thing that we found.
I'm not sure if that is applicable, but there are also like this stuff like probabilistic circuits, etc. They are larger
What do you mean, probabilistic?
circuits.
Yes,
They are
but
class
then,
of
then they would be straight line programs, so that there is no interesting control flow analysis that we could do. So the point was to be able to really try to mimic the control flow of the program and be able to analyze that. Otherwise, automation would be rather easy.
Okay. Thank you. So if there are no, there are questions.
Thanks, John.
Yeah, so I just had a question about the kinds of recursion you can handle. So can you handle cases like probabilistic divide and conquer, like a quicksort type thing, where the recursive call sizes are probabilistic?
I'd like to. So the question is about the kind of complication in the problems. So we tried, so quicksort is very complicated because we have to branch in both parts. So very complicated if you do it automatically, of course. We tried quick select, which is easier. We tried on versions of where we abstracted away all the complications and have kind of a very neat language like this. We can use the machinery, but at the moment we are hampered by our constraint solver. So we managed to get everything down to constraints which are obviously true, but for the moment our constraints are not usable, not so easy that S&T can solve them. We're working on this.
Okay, thanks.
Thank you.
Okay. So if there are no further questions, let's thank the speaker again.